Okay, I am going to go through setting up the simulation for this first project. So this is the analysis of the bracket, right? So this is pretty much a simple loading on this that you can do quite easily with the mechanics and materials methods we've talked about in chapter 1 with regards to like finding the stresses, right? So, I won't cover any of that or the details that are in the write up, but I'm just going to go through the steps of setting up the finite element model and then solving it and then looking at the post processing. Okay. So I'm going to go relatively quickly. So I assume that you kind of have a little bit of experience with Fusion. If you don't, you should probably do that first. And the good thing about the video is you can always stop and rewind it. So I'm not going to go real slow. Okay. All right. Okay. So here I have the bracket already. Now you're going to have to import it. So you can do file, open, and then pick off of your directory the file. Okay. So you can go through open from my computer and do all that. But I already have it up here. So this is what it is. So it's in design, right? And that's what it looks like, okay? All right, so we're going to do a finite element analysis on this. So that's going to be in simulation. So we're going to pick simulation. So we're going to go from design into simulation. And now it's going to ask us what type of study or type of simulation we'd like to do. And so we're going to do static stress. Everything we do in this class is going to be static stress, okay? Fusion's actually getting quite good at doing some reasonably sophisticated modeling, and so I encourage you all to take a look at it. And yeah, so but we will just be using static stress analysis in this class. So okay, fine. So click on create study, and that will create. You can see down here on this tree. Now we have study 1, static stress, and you can see it has materials, and then load cases. We'll have one load case, and in the load case you have the mesh as well as the boundary conditions, which are the loads and constraints. Okay, and we'll go through all those. All right, so Fusion, I think, tends to have this sort of workflow where you start at the top and move across, and so we'll do that. All right, simplify. A lot of times you have geometry that's got features that make it difficult to mesh, and you want it, but they don't really have any meaning with regard to the finite element analysis. So like really small pinholes or fillets or chamfers. And so in Simplify, you can remove those without really changing the model itself, because when you machine it, you want to have all those features in there. So you don't want to delete those from your part database, but you do want to like hide them from the finite element model. So it still keeps the associativity. And that's what Simplify does. Simplify does. In this particular case, I made the geometry such that it's you really don't need to simplify it. It's not that hard to mesh. Okay? So you don't need to do that. Okay, materials. There's already a material assigned to it. Okay? It's steel. So I think you'll see it here, right? So this is the material that was assigned to the model. We don't see any need to change that, so we'll keep that there. Okay, so it's the 1018 steel. Okay. And then, so now we move to the next thing, which is the constraints. So constraints are how are we fixing the body for the analysis. So constraints and loads are what I call boundary conditions, or what most people call boundary conditions when they do this sort of thing. And in fact, these sorts of assumptions of picking the right boundary conditions are absolutely essential to getting a correct or a good simulation. There's a lot of subtlety to it, and we won't go through all that because it's a little beyond the scope of this class, but you do have to be careful about what they physically are doing, okay? So in this case, our constraints are pretty simple, right? We're going to consider the constraints to be these bolt holes, if you will, okay? Okay, so now we're going to do structural constraints, and you can pick fixed or pin or frictionless. Okay, now if you think about a bolt, what happens is you tighten it down with a lot of bolt preload. So it's really not the circumferential surface of the bolt that stops it from moving. It's the force, the pressure cone underneath the head of the screw. So we're going to fix, and the surfaces we're going to fix are actually not going to be like these, but really, let's see if I can get it. Those surfaces where the head of the cap screw will come down and contact the bracket. Okay, so I picked those 4 surfaces. That's really all you should do. Those are the most probably appropriate for doing these bolted connections, unless we were to do contact and all that sort of stuff, which is with the actual preload. But that's not really needed for that. For this case, because we're not going to be too worried about the stresses right here. We're worried more about the stresses in the bracket part that goes, that tapers off to the circular bearing location. Okay, so we've got them all fixed. They're fixed in X, Y, and Z. You can click these on and off and allow them to move in those directions, but we're going to fully fix it. Okay, and there you go. So now they're all fixed. Just as a check, you really want to make sure that when you impose all your constraints, that the body cannot translate in any of the 3 directions or rotate about any of those 3 axes. It has to be fully constrained so that there's no rigid motion allowed. Okay? So that we've done that. It's actually over constrained, but that's fine. There's nothing wrong with it being over constrained. This is what we'll later talk about as being statically indeterminate, but finite elements has no issues with that. Okay, so we've got it constrained, and now if you kind of expand out this little constrained tree, you can see that it highlights those. So if you have multiple different constraints, you'll see them all listed here, but we're good. If you do want to edit them, you can click the little edit thing and go and edit them. I guess you can turn them on and off so you can't see them. And the check mark means that it's actually suppressed when you run the simulation. So sometimes you want to turn them on and off and just see the difference. But in this case, we're going to leave them on. Okay, so that's all the constraints we have. So we're done with the constraints. All right, now we're going to go to loads. So the loads we're going to do here is, a pin bearing onto this circular feature, okay? All right. Now, if you think about that, it's not as if, I know in the textbook we always draw forces as like a point force, but that's really not how forces are applied. Forces are always applied over a contact surface, okay? And in this case, it would be the pin contacting with the circular surface. As the pin deforms and that circular surface on the bracket deforms, the area that's in contact and then the pressure distribution of that contact will change. Again, you can do a more sophisticated analysis that exactly captures all that contact stuff, but there is a simple type of load that approximates that, and it's called a bearing load. So we'll look at that. So we're going to pick loads, and you can see here different types. One of them is a bearing load. So what that will do is put a pressure distribution along this, 180 degrees of this contact surface, like the upper half of this cone. It won't put any pressure on the bottom stuff. So it's as if the pin is being pulled. Okay, so we're going to pick the surface. All right. Now you can kind of see, I don't know, that icon's a little small, but if you look at that icon, you see it's kind of got the arrows drawn as the force is being applied, okay? So it'll put a distribution on there, but the total magnitude will equal the magnitude you apply. Okay, so it's actually acting in this sort of lateral direction. So we want to swing it over 90 degrees so that the force is actually pulling the bracket. And then we want to change the value. So we're not in metric units. We're in in English imperial units. So we're going to change the units to pound force. And I think in the document I said 1,500 pounds of force. Put in whatever's in the write-up. I don't have it in front of me now, but I think it was 1,500, okay? So obviously you can change that. And then we hit OK. And now it is applied there, okay? And if we expand out loads, you can see that that load is applied. All right, so now you've done all the boundary conditions, okay? In later exercises, I won't exactly tell you what the boundary conditions should be, the forces and the loads. I'm going to allow you to kind of explore that. But for now, this is just to kind of get you started, so I'm telling you exactly what to do here. All right, so we've got the materials, we've got it constrained, we have the loads applied. The last thing we have to do is mesh, okay? And so we're going to mesh this. So if you click on the little edit pencil, it has some parameters that allow you to change the mesh. You can change the size of the elements. You can either make that size based on the model, or you can give it an absolute size, like, I usually tend to use the model-based size. And you can scale mesh per part. I don't know exactly what that does, but you can fool around with those and see the different types of meshes you get. All right. Pretty much for these other advanced ones, it's not a bad idea to keep them where they are. Parabolic means they're second-order elements. I know that doesn't mean much to you now, but those are the preferred ones for linear static analysis. Do not change these to linear. Keep those at parabolic. This is on a circle. How many degrees will be spanned by the edge of one element. So, 30 degrees is probably not too bad. The other ones are basically about where it works. So that's not too bad. And let's mesh it and see what it looks like, okay? So we're going to generate the mesh. And there it goes. So it gives you some stats. There's a very much an art on meshing. It does have a very significant impact on your results, but again, I'm not going to get too much into it. But this is pretty reasonable, right? So we want to analyze the stresses in this region and a little bit in this sort of contact area, and from my experience, this probably is more than good enough with parabolic elements. One way you can check if you're not sure is you can then go back. You can run it with this mesh. Then you can run it again with a finer mesh and see if the results change. If the results change significantly, then probably the coarser mesh was not satisfactory, okay? But we won't do that sort of mesh study analysis here, mesh refinement analysis here. We'll just kind of go with this. And so if you generate a mesh that's roughly like this, it's probably good enough, okay? If your numbers come way off stress-wise than what you calculate by hand, maybe there is an issue with your mesh, okay, or your boundary conditions. But I think you'll do pretty well here. Okay, so we've got the mesh, we've got the materials, we've got the loads, we've got the constraints. So we should be good to go. So we're going to solve now. So you can do this check, and it'll tell you if something is missing, like you didn't put enough constraints on, or there's no forces, or the mesh isn't generated, or there's no materials assigned. But here you can say the study setup has all the information required. So we should be good to run. So fine. So we're ready to run this. So we're going to solve it now. So we go up here to solve, and then we hit solve. So Fusion's kind of cool. It computes things on the cloud. So even if you have kind of a meh computer at home, it'll still solve. It won't solve on your kind of questionable computer. It'll solve it up on the cloud, which is pretty reasonable. So I hit submit, and it's scheduling, and let's hope it goes pretty well. It shouldn't take long to run. It looks like it's going pretty fast. If you refine the mesh more, it might take longer. Okay. Like I said, it shouldn't really matter with regard to your computer. While this is solving, maybe I can just talk a little bit more about some of the features here, okay? So like I said before, really to get boundary conditions correct, almost always, if you think about it, forces and constraints are applied through contact, okay? So Fusion actually does have a really nice contact feature, so you can do contact automatically. Oh, it's solved, so now it's changed to the post-processing mode. And also, if you have, if we really wanted to get accurately resolve the stresses around these bolt holes, what I would probably do is model a base plate that this is connected to, and then use the bolt modeling feature in Fusion 360 to more accurately get that. Because really, that surface where the bolt is not rigid. It's going to deform a little bit because the bolt will deform a little bit. And not only that, the preload of the bolt will add some additional stresses into that region, okay? Again, these are things that are a little out of the scope of this class, but just so you're there. Okay, fine. So it's run. It's given us a factor of safety because it knows the yield stress of the material. And we can close this out, and we're good here. Okay, so here are our results. Okay, so it's deformed. The deformation's exaggerated. I think you can change this to be like actual. So here's the actual deformation. So you really can hardly see it. So showing the deformation is nice because, it gives you an idea if this deforms like how you'd expect it to. If it does something weird like swings around, you know that your constraints are probably, there's something goofy with them, okay? But that looks pretty reasonable. The fixed surfaces do seem to be fixed, and it's definitely deformed in the load path of that load. Okay, now let's look at what we got here. So it's plotting the factor of safety, right? And so that's the factor of safety to yield that we've talked about, okay? Let's look at the stress. So I'm going to change this to stress. You can also plot the displacement, the reaction forces, as well as the strains. So the reaction forces, let's look at that real quick. So you can see what that's doing is you see it's putting the reaction forces right on those surfaces where we had the constraints. So here are the reaction forces, the distributions there in newtons, but maybe you wanted to look at it in terms of pounds, and so it's there, okay? Very often you want to integrate that and get the actual reaction force, but that's a little beyond here. But okay, so let's look at the stresses, right? So we're going to look at the stresses. So there they are. Again, make sure you have the legend when you make plots of all this stuff. I believe if you go into your results tool, you can make the legend bigger, maybe, legend size. Because sometimes, oh, that's just weird. That's not really doing what I wanted to do. But there's probably a way you can change the font if we go in here. Oh, let's go back to here. But you want to make sure that it has... Wait, what's going on here? That when you take the picture and put it into your report, that you can see the numbers. Because without the numbers, this is meaningless. So basically, you can look here. Most of this is blue. So that means it's sort of in this area here of below 16 megapascals. All right. We're going to change the units to PSI. So now we're in PSI. And there's different types of stresses. So we're not quite there to discuss these. For now, well, the von Mises is like an effective stress. You'll cover that in design. But the way this bracket is, here is the X direction. So you could look at the normal stresses in the X direction. These will be close to the stresses you'd calculate by P over A. You could also get the shear stresses on the XY plane or the XZ plane. Where's XY? And those should be basically zero. And you can see they are basically zero because there's no shear loading in this bracket, right? All right, so let's go back to the normal XX stresses. Now, those are significant because it's being pulled in the X direction, so that makes sense. And so there you go. So you got some high stresses right around here. Those are probably due to the non-realistic fixed constraint there. If you actually had like a deformable bolt, it would ease up some of that stress. You also can see, obviously, that you get some peak stresses right where the hole is as well as at these fillets, right? And so if you were to change these fillets, make it bigger, you would see those stresses drop. But anyway, so for this exercise, I wanted you to look at these stresses sort of through cutting planes in here. So we need to be able to generate a cutting plane. So let's do that. So, and you can display it with the mesh if you want to. You can display the undeformed. You know what I mean? Probably. Usually we don't put the mesh on, and I would say, oh, no, we do want that at least. That's good. Okay, and then okay, so we need to do a cutting plane. So it's going to be under inspect and create slice plane. All right, so we're going to do a plane that's offset from, I asked you to find a cut plane that's 1 inch off of there. So you see, well, here it is. If we drag this little thing, it moves it out in the X direction. And so here it's giving us in millimeters, but I said to do 1 inch off of there, right? So I think we can just type in here 1 inch. And there you go. You can change like what it looks like on the cut surface. Sometimes it's a little confusing, you know, so probably. So, okay. Whoops. Wait, what is that doing? That's weird. Okay, so that one's not too bad. This one shows the traction vectors on there, okay? And here you can see the normal traction vectors are all in the X direction. There's no shear, right? If we were to load it like in the Y direction, you'd actually see shear tractions out there, okay? You know, you can leave those on or off if you want to. But, okay. Fine. So now you can see the stresses on here. It's pretty uniform, okay? If you look very closely, it is a little bit less at the edges and a little bit more in the middle. But it's pretty uniform, okay? And we can actually go in here and inspect and actually pick the numbers. So I think we can create, I always forget, create surface probes. Let's create, let's see what, I think create point probe. So we're going to pick a point. So you can pick the point. So these all should have the same X location. So it looks like you see the X dimension staying the same because that's the cut plane, right? So we can pick like one here. Oh, what is this doing? What is this doing? All right, I don't know what that's doing. Wait, maybe that's not what I thought it was. Okay, let's undo that. I think. Well, I don't know what's going on. Well, whatever. Let's if you do click point probe, at least if you drag your cursor over this surface, you can see the values of the stress that's being plotted. So it's showing you the values of the normal stress in the X direction. Okay, so this is the actual normal stress. And you can see up here at the edges, it's about 1,300 PSI. Oh, actually, I have it the wrong way. As we go down to the middle, it drops down to 400 and then goes back up to 1,300. So in the middle here, it stays pretty constant. 400 to 500 range, right? And, you know, that variance has to do with a little bit of the mesh, but mostly because, you know, the stress does vary across the cross-section. And in mechanics materials, we simplify the way we think of it by looking at the average stress, okay? So it's not quite the same, okay? But anyway, so that's how you can get those values, okay? So there you go. That's pretty much what you need to do this project. So you can get the values of stress from the finite elements on the cut plane by picking these values, and then you can compare those to your hand calculated, force over areas. If you want to actually look at the factor of safety here, you can just change the display from stress to factor of safety. And then again, you can drag the probe over the surface, and you can see it's pretty high here. It's staying at 15 the whole way, okay? You can see if we go over these higher spots, the factor of safety drops down. So, all right. So I think that's good. So, okay. So last thing, if you wanted to export your results, how do you do this? Results tool. You can do a summary report, and those are pretty cool to look at because you can see how they present the data. And I think, that's good to look at. It's probably not a bad way for you to consider putting into your report. You can also just do, what I usually do is just do a screen capture, to be honest with you. So, you can turn off the max, wait, how do you turn off the max min? Hide max min. And you can also hide that cutting plane if you want. You can go up here to, where is it? Results? Maybe it's under results. Slice planes. If I do this, does it... Okay, that turns off the plane. Okay, if I turn off the little eye, then it's still cutting the plane, but I don't see the actual plane. So that might be what you want to see. Maybe you want to plot it that way. And then I just do the screen capture, like on Windows, it's the Windows Shift S, and just, grab it. But when you do, make sure that you get the legend. Without this legend, right... It's meaningless because you need to know what the stresses are. First of all, you need to know what you're plotting. Sometimes students just plot the colors, and you don't know whether it's strain, displacement. Forget about what the values are. Okay, so it's really a meaningless exercise. So that's one thing you want to be careful of. The other thing you want to be careful of is when you present your results. Like I said before, the boundary conditions. How you choose those, very important. So you have to make sure you clearly explain in your report how you fixed it and put the loads on. Now, I know we're all going to do the same way, but you need to get in the practice of doing this, okay? All right. And also, what your mesh size is also important. So you might want to take a screenshot of the mesh and put that in there as well, okay? And maybe a screenshot of it uncut if you wanted to. You can turn off the cut and then take a picture of that, all right? All right, I think that's pretty much it. If you have any questions, like how to get this finally done, you can always post those in the discussion board, okay? So I think that's it.